This would have a momentum of -30, so I have a total momentum of -30. In the mass 2 reference frame, so we had mass 2 going to your left at 2 meters per second. Well, if you move along at 2 meters per second to your left, it looks like it's not moving at all. What would its velocity be? In that reference frame, what is mass 1's velocity? To get from here to here, I added 2, so I would add 2 there. So the momentum beforehand, this is 18, this is 0, and so I have a total of 18. What I'm looking for in the third technique is the zero momentum reference frame. How fast do I need to go as an observer in order for the total momentum to be 0? Well, let's do it out the long way to start with. Since all I'm doing when I shift from one reference frame to another is I subtract the same number from both sides. So here I subtracted 4 from both sides. Here to here I subtract -2 from both sides. So what I'm going to do is I start with 4. Let's see, I have 3 times 4 minus some shift plus 5 times -2 minus whatever that shift is equals 0. I'm trying to figure out how fast do I need to go as an observer, or what is my velocity as an observer so that my total momentum is 0. 12 minus 3v minus 10 minus 5v equals 0. 2 is equal to 8v, v is equal to 0.25. Where have we seen that before? Pardon?
The first equation that we did?
Oh, the first problem? Yes. It is the solution of the perfectly inelastic collision. That is always the case. For the one-dimensional problem. These are all one-dimensional collision problems. You get to two-dimensional, it's more complex than this. So what I'm going to do is I'm going to be in that reference frame, called the zero momentum frame. And I'm going to subtract 0.25, so subtract 0.25 from that, I get 3.75. Subtract 0.25 from that, I get -2.25. Times 4. So that'll be 15 minus subtract 0.25 is what we had over there, -2 minus 0.25. That times 5, why is this, something's off? Oh, because that's not 15. I multiply times 4, not 3. The mass is 3. 10.5, 11.25. And then 5 times that. Well, 5 times 2 is 10, 5 1/4, 5 times 1/4 is 1 1/4, so plus -11.25 equals 0. All right, that's what we're looking for. So we start out with, I'm in the zero momentum frame. I'm now in the zero momentum frame. I have my 3 kilogram mass heading to the right at 3.75 meters per second. I have my 5 kilogram mass heading to the left at 2.25 meters per second. After the collision, I need the total momentum and the total kinetic energy to stay the same. What is a simple solution that would do that besides the original problem? Because remember, for kinetic energy to stay the same, if the speeds stay the same, we're good. My total momentum is 0. So after the collision, what is a velocity for the 3 kilogram mass and the 5 kilogram mass that will give you the exact same total momentum and the exact same total kinetic energy? There's always that. I hope you at least recognize kinetic energy just cares about speed. My momentum, if I just flip the signs of those two velocities, if this becomes negative and that's positive, what's my total momentum now? Yes. That's negative and that's now positive. It's still 0. All I have to do is flip the signs. So if this is now going to the left at 3.75 meters per second, and this is now going to the right at 2.25 meters per second, then I have, my kinetic energy has got to be the same because they both have the same speeds they had before. My momentum is still 0 because all I've done is just, it's like switching positive to go that way, in a sense. The only thing left to do is to put it back into the original frame of reference. So this is the original problem here, then they collide. This is now negative 3.75, this is positive 2.25. To get from here to here, I subtracted 0.25. To get out of it, I do the opposite. So since I subtracted 0.25, I now add 0.25. And I get 2.5 and negative 3.5, which is what I got the other 2 times. Showing it to you in sort of the way that I would do it, and maybe even getting one with nice answers in the end. That'll work. So if I have a 3 kilogram mass going to the right at 4 meters per second, which will look somewhat familiar, and a 1 kilogram mass going to the left at 6 meters per second. This is the way I would solve it using that third technique. I have 12 minus 6 is equal to 6, which is equal to 4. V equals 1.5. First thing I do is figure out what is the perfectly inelastic collision solution. This starts out with 4, that starts out with negative 6. I subtract 1.5, so I get 2.5 and negative 7.5. So this is lab frame, shift, 0 momentum frame. There's now the collision. Negative 2.5, positive 7.5. This is after. And then the shift back. I subtracted 1.5 there, so I now add 1.5. And final 9 meters per second. Negative 1 meter per second. Answer. The advantage of this method, to me, is it's a whole lot simpler. The biggest complication is right there, calculating that. And in a lot of test problems, not the Rube-Goldberg test, but in a lot of test problems, I have 2 objects heading towards each other. Part A, what's the perfectly elastic collision velocity afterwards? And part B, what's the perfectly elastic collision solution? The disadvantage is it's a little bit more abstract. Of the three methods, pick one. Know how to use it. I don't specify which one to use on the test. I haven't, I don't expect to. Know how to do one of them. Know how to do all three of them would be great, but just please don't mix and match when you get to the test. Questions? Yes?
For the test, are we going to have like a 2D question like this? Or is it
If I
like,
give you a two-dimensional problem, then what I basically do is say set up the equations. So you'll have three unknowns because you'll have initial final velocities each in 2 dimensions. And yeah, so I have to give you some piece of information so that there's only 3 unknowns. But it usually set up the equations and just stop it there. Because the rest is potentially tedious math or enjoyable math. I've done tests before where I say just set up the equations and have had some students just go ahead and solve it because they enjoy it or didn't read carefully, one or the other. You're anxious about, you're thinking, hey, what lab are we gonna do? Are we gonna do conservation of momentum? No, we'll do conservation of energy. Oh, I guess it's the shortest of all the labs, so that's one reason why I'm not worried about time. There is one other bit that I probably should discuss I mentioned it before last week. But one of my 2 most obscure clues, if someone suddenly buys you flowers, that is called? Physicists do not go that route. I'm gathering none of you were watching perfume commercials in the 70s.
What gives you that idea?
Just gut feeling. Impulse. Don't even know if it's still made, but it was a perfume commercial. Someone suddenly buys you flowers, that's called impulse.
Will that be a question on the process?
No,
Should be.
it should be,
Can
yeah.
be.
All right, so what is, from our point of view, what is the momentum of the marker? Why?
it's not moving?
All right, I have this marker, momentum is 0, I let go. As it falls, is the momentum still 0?
No.
Is momentum therefore conserved in the marker? But I was talking about book conservation momentum, yet there's a very simple example where momentum clearly is not observed. So why was momentum not conserved there, but I make some bold claim like that, or in particle physics where momentum is conserved?
Because it's not elastic? Because it's not elastic?
Not that. In this problem right here, what are the forces, what are the source of the forces acting on the 3 kilogram mass? What's exerting a force on the 3 kilogram mass?
When they hit
Yeah,
the other,
the other one.
yeah.
So, probably to make it more general, when they interact. In this case, it's an actual collision. But yes,
Is it because that only had one force acting against it, that would be no momentum?
so what about when I had the marker? How many forces did I have acting on it?
Just you and gravity? What does gravity have?
Well, once I let go.
Just gravity?
Acceleration, gravity,
Looking for the force.
gravitational force.
Yeah, otherwise known in this case.
Wait.
Thank you. All right, what's causing it?
You dropping it? Or the weight of the marker?
What's causing the weight of the marker? Though I appreciate your thinking I had something to do with the weight of the marker. I don't have those powers.
Mass and weight.
What causes the weight?
Acceleration due to gravity.
What source, what object causes the weight of that marker?
Earth.
Sorry?
Earth.
Yes, the planet. So the difference is, in this case right here, we took both of them into account. In this case right here, I was looking at just the marker, but there was another object involved.
The ground.
So if the system, if I'm taking into account everything, there's no outside influence. All the masses that are involved in it, I am dealing with.
So
That is called a closed system. In a closed system, momentum is conserved. In the case of the marker, probably can guess what it's called.
open system.
If there is an outside influence, if there is some object causing a force on the objects in my system, that is an open system. There's outside influence coming in. Momentum is not conserved. So if I took the Earth marker system, I could have momentum conserved, because as the marker fell, I'm sure you noticed that the Earth came up probably about half the diameter of or otherwise known as the radius of a nucleus. Maybe the radius of a proton, but not that Earth shape.
Totally perceptible, yes.
Say it again?
So that's totally perceptible, yes.
Oh, yeah. But if I'm looking at an open system, there's some outside influence. So if I'm looking at just the marker, it was an open system. If I did marker Earth, it's a closed system.
Okay, well, what would open system be again?
There are outside influences. There are things influencing the objects in the system. From outside.
Like the Earth? Gravity?
Yes. Yeah, so in a closed system, momentum is conserved. In an open system, there is a change in momentum. And that change in momentum is called impulse. Impulse is the change in momentum delta V, which is also equal to force times time. Now, if I ask you to find the impulse, which one do you use? Well, whichever one you have the information for. If I give you mass, final, initial velocity, yeah, that's the simpler one. If I tell you the force acting on the object and how long it acts, yeah, that's the simpler one. They are equal to each other, so if I ask you to find impulse, pick one. Or do the one that you can do. So over here, if we look at this 3 kilogram mass, as a system by itself, just looking at that, yes, it's momentum change. It went from 12 to -3. The impulse acting on the 3 kilogram mass would be -15 Newton seconds. Over here, I went from -6 to 9. -6 Descartes to 9 Descartes. My change in momentum, positive 15 Newton seconds. So what if that lost this game? On that note, let's head on down to